sklearn multiclass. Description: Multiclass classification is a type of supervised learning where the goal is to predict the class label of a data point from a set of more than two classes. In contrast to binary classification, where the model needs to distinguish between two classes, multiclass classification tackles the challenge of categorizing data into multiple distinct classes. Inputs: data. This refers to the input features used for training and predicting the class labels. It can be a tabular dataset with numerical and categorical features, or a dataset of images, text, or other types of data. The features should be carefully chosen to provide sufficient information for the model to distinguish between the different classes. Target: this represents the true class labels corresponding to each data point. It's a set of labels belonging to different categories, typically represented as categorical or numerical values. For example, if classifying different types of animals, the target could be dog, cat, bird, etc. Outputs: predictions. The model's output, representing the predicted class labels for new data points. It can be a numerical array, a list of class names, or probability scores for each class. Model: the trained model itself, which can be used for making predictions on new data. This is essential for deploying the model and using it for future classification tasks. Steps: data preparation. This involves cleaning, pre-processing, and transforming the data to make it suitable for the chosen classification model. This can include handling missing values, converting categorical variables to numerical values, and scaling numerical features. Model selection: there are various multiclass classification algorithms available in scikit-learn, each with its own strengths and weaknesses. Examples include logistic regression, support vector machines (SVM), decision trees, random forests, naive Bayes, and more. Choosing the right model depends on the nature of the data, the desired performance, and computational resources. Model training: the chosen model is trained on the prepared data, aiming to learn the relationship between the features and the target class labels. This process involves finding optimal model parameters that minimize the difference between predicted and actual labels. Model evaluation: the trained model's performance is assessed using appropriate evaluation metrics, such as accuracy, precision, recall, F1 score, and confusion matrix. This helps understand the model's effectiveness in classifying different classes and identify areas for improvement. Model deployment: once satisfied with the model's performance, it can be deployed for making predictions on new, unseen data. Metrics: accuracy: this measures the overall proportion of correctly classified samples. It's calculated as the ratio of correct predictions to the total number of predictions. Precision: this measures the proportion of correctly predicted positive samples among all samples predicted as positive. It's useful for evaluating models that aim to minimize false positives. Recall: this measures the proportion of correctly predicted positive samples among all actual positive samples. It's useful for evaluating models that aim to minimize false negatives. F1 score: this metric combines precision and recall into a single value, providing a balanced measure of a model's performance. It's especially useful when dealing with imbalanced datasets. Confusion matrix: this visualizes the performance of a classification model by showing the number of true positives, true negatives, false positives, and false negatives for each class. It helps to understand the model's strengths and weaknesses in classifying different classes. Visualization plots: confusion matrix plot: this visualizes the performance of a classification model by showing a number of true positives, true negatives, false positives, and false negatives for each class. It helps to understand the model's strengths and weaknesses in classifying different classes. ROC curve. This plots the true positive rate against the false positive rate for different classification thresholds. It helps to visualize the trade-off between sensitivity and specificity of the model. Precision recall curve. This plots the precision against the recall for different classification thresholds. It helps to visualize the trade-off between minimizing false positives and minimizing false negatives. Fine-tune parameters. Regularization parameter. This controls the strength of regularization, which helps prevent overfitting by penalizing complex models. Regularization techniques like L1 or L2 can be used to simplify the model and improve its generalization performance. Learning rate. This controls the step size taken during the optimization process. A smaller learning rate can lead to slower convergence but potentially a better solution. Number of trees in ensemble methods like random forests. This parameter determines the number of decision trees used in the ensemble. Increasing the number of trees can improve the model's accuracy but may also increase computational complexity. Uncertainty methods. Confidence scores. These are probabilities assigned by the model to each class for a given data point. Higher confidence scores indicate a higher probability of the predicted class being correct. Prediction intervals. These provide a range of values around the predicted class, indicating the model's uncertainty about the prediction. Wider intervals suggest higher uncertainty. Challenges and fixes. Challenge 1. Overfitting. This happens when the model learns the training data too well and fails to generalize to new data. Sample use case that resulted in challenge 1. A model trained on a small dataset with many features may overfit, resulting in poor performance on unseen data. Fixes to challenge 1. Use regularization techniques, such as L1 or L2 regularization, to penalize complex models. Employ cross-validation to evaluate the model's performance on unseen data. Consider reducing the number of features or using feature selection techniques to simplify a model. Challenge 2. Imbalanced dataset. This occurs when the classes in the training data are not represented equally, leading to biased models that favor the majority class. Sample use case that resulted in challenge 2. A dataset with a large number of examples from one class and only a few examples from another class will lead to a model that is more likely to predict the majority class. Fixes to challenge 2. Use techniques like oversampling, undersampling, or synthetic minority oversampling techniques to balance the dataset. Consider using class weights in the model to give more importance to the minority class. Evaluate the model using appropriate metrics, such as F1 score, that are less sensitive to class imbalance. Challenge 3. High dimensionality. This arises when the number of features in the data is very large, leading to computational challenges and potentially overfitting. Sample use case that resulted in challenge 3. A dataset with thousands of features may be difficult to process and can lead to a model that is overly complex and prone to overfitting. Fixes to challenge 3. Use dimensionality reduction techniques, such as principal component analysis (PCA) or linear discriminant analysis (LDA), to reduce the number of features while preserving important information. Employ feature selection techniques to identify and select the most relevant features for a classification task. Challenge 4. Data sparsity. This occurs when there are many missing values in the data, leading to inaccurate models or unreliable predictions. Sample use case that resulted in challenge 4. A dataset with many missing values for certain Features will make it difficult for the model to learn patterns and make accurate predictions. Fixes to challenge 4. Impute missing values using techniques like mean imputation, median imputation, or k-nearest neighbors imputation. Use models that are robust to missing values, such as decision trees or random forests. Challenge 5. Interpretability. Some multi-class classification models, such as neural networks, can be difficult to interpret. Sample use case that resulted in Challenge 5. A neural network with many layers and hidden units can be difficult to understand, making it challenging to explain the model's predictions. Fixes to Challenge 5. Use techniques like feature importance analysis to understand which features are most influential in the model's predictions. Employ model simplification techniques, such as pruning or reducing the complexity of the model. To improve interpretability, consider using interpretable models, such as decision trees or rule-based models, which are easier to understand. sklearn Multiclass 1V's REST classifier. Description. The 1V's REST classifier strategy in scikit-learn is a method for handling multiclass classification problems by breaking them down into a series of binary classification problems for each class in your dataset. It trains a separate binary classifier that distinguishes instances belonging to that class from instances belonging to all other classes. Inputs: X feature matrix or array, where each row represents an instance and each column represents a feature. Y target labels or array, containing the true class labels for each instance. Outputs: model a trained 1V's REST classifier object that can be used to predict class labels for new data. Predictions: predicted class labels for new data instances. Steps: 1. Decomposition. The 1V's REST classifier strategy divides the multiclass classification problem into a set of binary classification problems for each unique class label in your dataset. It creates a separate binary classification problem where instances belonging to that class are labeled as +1 and all other instances are labeled as -0. 2. Individual binary classifier training for each of the binary classification problems. A binary classifier, e.g., logistic regression, SVC, decision tree classifier, is trained using the selected estimator. 3. Prediction. During prediction, the trained classifiers for each class are applied to the new data. The classifier that outputs the highest confidence score or probability determines the predicted class label for a given instance. Metrics: accuracy, the proportion of correctly classified instances. Precision, the proportion of positive predictions that were actually positive. Recall, the proportion of actual positive instances that were correctly predicted. F1 score, a harmonic mean of precision and recall. Visualization plots. Confusion matrix, a visual representation of the predicted vs. actual class labels. Precision recall curve plots the precision and recall for different thresholds on the predicted probabilities. ROC curve plots the true positive rate sensitivity against the false positive rate one. Specificity at different thresholds. Fine-tune parameters. Estimator, the binary classifier to be used for each binary classification problem, e.g., logistic regression. SVC. Decision tree classifier. N-jobs, the number of jobs to run in parallel. Uncertainty methods. Confidence scores. The 1V's REST classifier can provide confidence scores, e.g., probabilities for each predicted class label, which can be used to assess uncertainty. Challenges and fixes. Challenge 1. Imbalanced datasets. When classes are imbalanced, the 1V's REST classifier might favor the majority class. Sample use case that resulted in challenge 1. You have a dataset with 90 instances belonging to class A and 10 instances belonging to class B. The 1V's REST classifier might make more accurate predictions for class A due to the majority of training data being from that class. Fixes to challenge 1. Data resampling techniques like oversampling the minority class or undersampling the majority class can help balance the dataset. Class weighing. Modifying the cost function of the binary classifiers to give more weight to the minority class can address class imbalance. Challenge 2. Computational complexity. Training multiple binary classifiers can be computationally expensive, especially for large datasets with many classes. Sample use case that resulted in challenge 2. You have a dataset with 100 classes and 1 million instances. Training a 1V's REST classifier with a complex estimator like a support vector machine can take a long time. Fixes to challenge 2. Parallel processing. Utilizing multiple cores or processes can speed up the training process. Simplifying the estimator. Choosing a simpler estimator, such as a decision tree, can reduce computational complexity. Feature selection. Reducing the number of features can also improve training speed. sklearn Multiclass 1V's 1 classifier. Description. The 1V's 1 classifier strategy is a method for multiclass classification. It constructs one binary classifier for every pair of classes. To make a prediction, each binary classifier predicts the class for the given sample, and the class with the most votes is chosen. Inputs. X. The input features for the training data. This is typically a 2D array, where each row represents a sample and each column represents a feature. Y. The target labels for the training data. This should be a 1D array with the same length as X, where each element represents the class label of the corresponding sample. Outputs. Predictions. A 1D array of class labels for the given input samples. Probabilities. Optional. A 2D array of predicted probabilities for each class. Steps. Training. The 1V's 1 classifier trains a binary classifier for each pair of classes. For each pair, the training data is filtered to include only the samples belonging to those two classes. The chosen binary classifier is then trained on this filtered data. Prediction. To predict the class label for a new sample, the 1V's 1 classifier uses each binary classifier to make a prediction. The class that is predicted most often across all binary classifiers is chosen as the final prediction. Metrics. Accuracy. The ratio of correctly classified samples to the total number of samples. Precision. The ratio of correctly classified positive samples to the total number of samples predicted as positive. Recall. The ratio of correctly classified positive samples to the total number of actual positive samples. F1 score. The harmonic mean of precision and recall. Visualization plots. Confusion matrix. A visualization that shows the number of correctly and incorrectly classified samples for each class. Precision recall curve. A plot that shows the trade-off between precision and recall for different thresholds. ROC curve. A plot that shows the relationship between the true positive rate and the false positive rate for different thresholds. Fine-tune parameters. Estimator. The binary classifier to be used for each pair of classes. The default is a logistic regression. N jobs. The number of jobs to run in parallel. This can be used to speed up the training process. Decision function shape determines the shape of the decision function. Can be over 1 vs rest or over 1 vs 1. Uncertainty methods. Confidence scores. The 1 vs 1 classifier can provide confidence scores for each class, which can be used to measure the uncertainty of the prediction. Challenges and fixes. Challenge 1. Overfitting. If the binary classifiers are overfit to the training data, they may not generalize well to new data. Sample use case that resulted in challenge 1. If the training data is small or imbalanced, the binary classifiers may overfit to the training data. Fixes to challenge 1. Use regularization techniques such as L1 or L2 regularization to prevent overfitting. Challenge 2. Computational cost training. A large number of binary classifiers can be computationally expensive. Sample use case that resulted in challenge 2. If the number of classes is large, training a 1 vs 1 classifier can be computationally expensive. Fixes to challenge 2. Use a smaller number of classes or reduce the complexity of the binary classifier. sklearn multiclass output code classifier. Description: the output code classifier is a multiclass classification strategy that reduces the multiclass problem to a series of binary classification problems. It works by creating a code for each class, which is a binary vector with a 1 in the corresponding position and zeros elsewhere. For example, if there are 3 classes, the code for class 1 would be 1, 0, 0. The code for class 2 would be 0, 1, 0. And the code for class 3 would be 0, 0, 1. The classifier then trains a binary classifier for each bit in the code and predicts the class by taking the code with the highest score. Inputs: X the training data, A 2D array of shape and samples, N features, Y the target values, a 1D array of shape and samples. Outputs: Y pred the predicted target values, a 1D array of shape and samples. Y score the decision function scores for each class, a 2D array of shape and samples. N classes. Steps: encode the target values into a binary code. Train a binary classifier for each bit in the code. Predict the class by taking the code with the highest score. Metrics: accuracy, the percentage of correct predictions. Precision, the percentage of true positives among all positive predictions. Recall, the percentage of true positives among all actual positives. F1 score, the harmonic mean of precision and recall. Visualization plots. Confusion matrix, a table that shows the number of true positives, true negatives, false positives, and false negatives for each class. ROC curve, a plot that shows the trade-off between true positive rate and false positive rate for different classification thresholds. Fine-tune parameters. N jobs, the number of jobs to run in parallel. Random state, the random seed to use for the random number generator. Code size, the number of bits in the code for each class. Uncertainty methods. Confidence scores, the decision function scores for each class can be used as a measure of confidence. Entropy, the entropy of the probability distribution over the classes can be used as a measure of uncertainty. Challenges and fixes. Challenge 1, the output code classifier can be sensitive to the choice of code size. Sample use case that resulted in challenge 1: if the code size is too small, the classifier may not be able to distinguish between different classes. Fixes to challenge 1: increase the code size until the classifier achieves good performance. Challenge 2, the output code classifier can be computationally expensive to train, especially for large datasets. Sample use case that resulted in challenge 2: if the dataset has millions of samples and hundreds of classes. The training time can be very long. Fixes to challenge to use a smaller code size or use a faster binary classifier, such as a linear SVM. sklearn multi-output. Description: explain in detail. Multi-output regression is a type of supervised learning where a model learns to predict multiple target variables simultaneously. It's used when you have multiple correlated outputs that need to be predicted based on a set of input features. Inputs. Input 1. Explain in detail. The input data is usually a 2D array or a pandas data frame containing features that will be used to predict the target variables. Each row represents a sample, and each column represents a feature. Input 2. Explain in detail. The target variables are also provided as a 2D array or a pandas data frame, where each row corresponds to a sample and each column corresponds to a different target variable. Outputs. Output 1. Explain in detail. The model predicts multiple target variables, and the output will be a 2D array or data frame containing the predicted values. Each row represents a sample, and each column corresponds to a different predicted target variable. Output 2. Explain in detail. In addition to the predictions, you can obtain information about the model's performance, such as the R-squared score for each target variable or the mean absolute error for the entire multi-output prediction. Steps. Step 1. Explain in detail. First, you need to select a multi-output regression algorithm, such as random forest, gradient boosting, or multi-output linear regression. Step 2. Explain in detail. Next, you need to train the model on your input data and target variables. Metrics. Metric 1. Explain in detail. R-squared R2 score for each target variable. This metric measures how well the model explains the variance of each individual target variable. A higher R-squared value indicates a better fit. Metric 2. Explain in detail. Mean absolute error made. This metric calculates the average absolute difference between the predicted and actual values for each target variable. A lower may indicates better accuracy. Visualization plots. Visualization plot 1. Explain in detail. Scatter plots for each target variable. You can visualize a relationship between the predicted and actual values for each target variable using scatter plots. This helps to understand the model's performance and identify potential areas for improvement. Visualization plot 2. Explain in detail. Residual plots. You can also plot the residuals differences between predicted and actual values for each target variable to check for patterns or trends that might indicate problems with the model. Fine-tune parameters. Parameter 1. Explain in detail. Number of estimators for tree-based models. This parameter controls the number of trees in the ensemble. Increasing the number of estimators can improve the model's accuracy but also increases training time. Parameter 2. Explain in detail. Learning rate for gradient boosting models. This parameter controls the step size taken during the optimization process. A smaller learning rate may lead to better accuracy but requires more iterations. Uncertainty methods. Uncertainty method 1. Explain in detail. Confidence intervals. You can calculate confidence intervals for each predicted target variable to estimate the uncertainty in the predictions. Uncertainty method 2. Explain in detail. Predictive variance. Some models provide a measure of a variance of the predictions, which can be used to assess the uncertainty. Challenges and fixes. Challenge 1. Explain in detail. Data imbalance. If the target variables have significantly different distributions, the model may favor the target variable with more data points. Sample use case that resulted in challenge 1. A dataset where one target variable has a very wide range of values and the other has a narrow range. Fixes to challenge 1. Normalize the target variables. Rescale the target variables to have similar ranges, which can help the model learn equally well for all variables. Challenge 2. Explain in detail high correlation between target variables. When target variables are highly correlated, the model may struggle to learn separate relationships for each variable. Sample use case that resulted in challenge 2: a dataset where two target variables are almost identical. Fixes to challenge 2. Feature engineering. Try creating new features that capture the combined information of highly correlated target variables. Dimensionality reduction. Consider using techniques like PCA to reduce the number of target variables. sklearn multi-output classifier chain. Input 1. Explain in detail classifier chain accepts a multi-output estimator like a multi-label classifier and an ordering of the outputs. It chains together individual classifiers, each one learning to predict a single output label. The outputs from previous steps are used as additional input features for subsequent steps. The ordering of the outputs determines the chain of predictions. The first classifier in the chain only receives the original input features. Each subsequent classifier gets the original input features plus the predicted outputs from the previous classifiers. This allows the chain to take advantage of dependencies between the output labels. The output of classifier chain is a multi-dimensional array of predictions, where each column corresponds to an output label and each row corresponds to a data point. The predictions for each output label are generated by the corresponding classifier in the chain. Step 1. Explain in detail. Initialize the classifier chain with a multi-output estimator and an ordering of the outputs. The data is then fed into the chain, and each classifier makes its predictions in order. Metric 1. Explain in detail accuracy, precision, recall. F1 score are common metrics used to evaluate the performance of multi-label classification models. Other metrics specific to multi-output models include Hamming loss, subset accuracy, and ranking loss. Visualization. Plot 1. Explain in detail confusion matrix for each individual classifier in the chain, illustrating the true positives, true negatives, false positives, and false negatives. Receiver operating characteristic ROC curves or precision recall curves can be generated for each individual classifier in the chain. The choice of base estimator, e.g., a random forest logistic regression, has a significant impact on the performance of the classifier chain. The ordering of the outputs can affect the performance of the model, as the chain assumes that there is a causal relationship between the labels. Confidence scores for each prediction can be obtained by averaging the probabilities across different classifiers in the chain. Bayesian methods can be employed to estimate uncertainty in the predictions, especially when the base estimator is a probabilistic model. Poor performance if the output labels are not causally related. When predicting multiple medical diagnoses, there might not be a clear order in which the diagnoses are made. Consider using a different multi-output approach like a multi-label classifier without chaining. Overfitting if the chain is too complex. A long chain with multiple classifiers can overfit to the training data. Use regularization techniques on the base estimators, e.g., L1 or L2 regularization, or employ ensemble methods to reduce overfitting. sklearn multi-output regressor. A 2D array of training data with each row representing an instance and each column representing a feature. A 2D array of target values for each training instance. A 2D array of predicted target values for each instance. The multi-output regressor class is initialized with a base estimator. This estimator can be any model that can be used for regression, such as a random forest, gradient boosting, or linear regression model. The fit method is called on the training data and target values, which trains the base estimator on the training data. The predict method is called on new data to generate predictions for each target variable. The prediction for each target variable is made independently using the corresponding trained base estimator. R squared, mean squared error MSE, mean absolute error MA, root mean squared error RMSE, scatter plots, residual plots, prediction error distribution plots. The parameters of the base estimator can be fine-tuned to improve the performance of a multi-output regressor model. For example, the number of trees in a random forest or the depth of the tree in a decision tree can be adjusted. The njobs parameter can be adjusted to specify the number of cores to use for parallel processing. Setting this to -1 will use all available cores. Confidence intervals, prediction intervals, overfitting. The model may overfit to the training data, resulting in poor performance on unseen data. A scenario where a model trained on a small dataset with complex features leads to overfitting. Use regularization techniques such as L1 or L2 regularization to penalize complex models. Increase the size of the training dataset. Multicollinearity. When multiple input features are highly correlated, it can lead to unstable predictions and difficulty in interpreting the model. A scenario where multiple features are measuring similar aspects of the data, leading to high correlations. Fixes to challenge to use feature selection techniques to remove redundant features. Regularize the model to prevent overfitting. sklearn multi-output classifier. Description. Explain in detail. The multi-output classifier is a scikit-learn estimator that combines multiple estimators to predict multiple target variables, each of which may be a different type. It handles multi-output classification problems, where each sample has multiple target variables, each of which can be a discrete label. Inputs. Input 1. Explain in detail the input data. Typically a 2D array of shape n samples. N features, where each row represents a sample and each column represents a feature. This data should be compatible with the chosen base estimator. Input 2. Explain in detail the target data. A 2D array of shape n samples. N outputs, where each row represents a sample and each column represents a target variable. The target values should be discrete labels for each output. Outputs. Output 1. Explain in detail a 2D array of shape n samples. N outputs, containing the predicted target values for each output. Output 2. Explain in detail each element in the output array represents the predicted label for the corresponding output variable and sample. Steps. Step 1. Explain in detail the multi-output classifier takes an array of estimators as input. Each estimator is used to predict a single target variable. The estimators can be of any type that supports the fit and predict methods, such as decision tree classifier, random forest classifier, or logistic regression. Step 2. Explain in detail during training. The multi-output classifier trains each estimator independently on the corresponding target variable. Metrics. Metric 1. Explain in detail. Accuracy measures the proportion of correctly predicted labels for each output variable. It's often calculated as the average accuracy across all outputs. Metric 2 explain in detail. F1 score measures the harmonic mean of precision and recall for each output variable. This metric is useful for imbalanced datasets. Visualization plots. Visualization plot 1 explain in detail confusion matrices for each output variable. A confusion matrix can visualize the performance of the classifier by showing the number of true positives, true negatives, false positives, and false negatives. Visualization plot 2 explain in detail feature importance plots if the base estimators support feature importance. You can visualize the importance of each feature for each output variable. Fine-tune parameters. Parameter 1 explain in detail estimator parameters. You can fine-tune the parameters of the base estimators used within the multi-output classifier, such as the number of trees in a random forest classifier or the regularization strength in a logistic regression. Parameter 2 explain in detail n jobs. This parameter controls the level of parallelism in the training process. Setting it to -1 utilizes all available CPU cores for faster training. Uncertainty methods. Uncertainty method 1 explain in detail confidence scores. Some base estimators, like logistic regression, provide confidence scores for each prediction. This can be used to estimate uncertainty. Uncertainty method 2 explain in detail ensemble methods using an ensemble of estimators within the multi-output classifier, such as random forest classifier, can provide an indication of uncertainty through the variance of predictions across different estimators. Challenges and fixes. Challenge 1 explain in detail data imbalance if the target variables have unbalanced classes. The performance of the multi-output classifier might be biased towards the majority class. Sample use case that resulted in challenge 1: a dataset with a target variable where one class has 90 of the data and the other class has 10. This might lead to the classifier predicting the majority class more frequently. Fixes to challenge 1. Use cost-sensitive learning. Assign different costs to misclassifications to penalize errors on the minority class more heavily. Oversampling. Increase the number of samples from the minority class to balance the dataset. Undersampling. Decrease the number of samples from the majority class to balance the dataset. Challenge 2 explain in detail high dimensionality if the number of features is very high. The multi-output classifier may suffer from the curse of dimensionality, leading to poor performance. Sample use case that resulted in challenge 2: a dataset with thousands of features but a limited number of samples. Fixes to challenge 2. Feature selection. Reduce the number of features by selecting the most relevant ones for each output variable. Dimensionality reduction. Apply techniques like principal component analysis (PCA) or linear discriminant analysis (LDA) to reduce the dimensionality of the input data. sklearn multi-output regressor chain. Description. The regressor chain class in scikit-learn sklearn implements a multi-output regression strategy that treats the prediction of multiple target variables as a chain of dependent regressions. This means that the prediction of each target variable relies on the predictions made for the preceding target variables in the chain. Inputs. X a 2D array representing the input features. Each row corresponds to a sample, and each column represents a feature. Y a 2D array representing the target variables. Each row corresponds to a sample, and each column represents a target variable. The number of columns in Y should match the number of estimators in the chain. Outputs. Ypred a 2D array containing the predicted target variables. Each row corresponds to a sample, and each column represents a target variable. Steps: initialize the regressor chain object with a base regressor and the order of the target variables. Train the chain by fitting it to the input features and target variables. Predict the target variables for new input features. Metrics: R² measures the proportion of variance in the target variable explained by the model. Mean absolute error may calculates the average absolute difference between the predicted and actual values. Mean squared error MSE calculates the average squared difference between the predicted and actual values. Visualization plots. Residual plots to visualize the difference between predicted and actual values for each target variable. Scatter plots to visualize the relationship between the predicted and actual values for each target variable. Fine-tune parameters. Base estimator. The base estimator to use for each step in the chain. This can be any regression estimator from scikit-learn, such as linear regression, decision tree regressor, or random forest regressor. Order. The order in which to predict the target variables. This should be a list of integers representing the indices of the target variables. Uncertainty methods. Confidence intervals can be calculated for the predicted values based on the uncertainty of a base estimator. Challenges and fixes. Challenge 1. Overfitting on the training data, leading to poor generalization performance on unseen data. Sample use case that resulted in challenge 1. When the training data is small or noisy, the chain might learn the specific patterns of the training data too closely, resulting in overfitting. Fixes to challenge 1. Regularization. Adding a penalty term to the loss function of the base estimator can prevent overfitting. Early stopping. Stopping the training process before the model reaches convergence can prevent overfitting. Challenge 2. The order of the target variables can significantly impact the performance of the chain. Sample use case that resulted in challenge 2. If a target variable is highly dependent on another target variable, it might be beneficial to predict the dependent variable first. Fixes to challenge 2. Experiment with different orders. Try different combinations of target variable orders to find the best configuration for your specific problem. Feature engineering. Create new features that capture the relationships between the target variables to improve the performance of the chain.